Yeah, and since this, especially the second recursive step here, is a little bit tricky, maybe on the first glance, or hard to comprehend, let's have a look at this a little bit closer and see the intuition behind. So once again, we just look at the last recursive step here. Yeah. So because this one here is easy, I think. Well, if the last so here, if the last elements match, we just have to look for the prefix. Yeah. We don't have to spend any edit operation to match them, yeah? To transfer Q into S, because this is already a match. Yeah, so this one here is the interesting part. Let's have a look, a closer look here. So once again, this is the formula here. So we have three options once again. The first one is that we substitute in order to transfer Q into S. We can substitute, and the last part here, the last elements are different. So take a look at this one here. So the last part here, last Q, is different to last S. So we have three options. We could first of all substitute Q by or last of Q by last of S. Yeah, so that would be the first case here. So we substitute it, which gives us one operation plus the cost that we need to match the prefix of Q without the last to the prefix of S without the last, obviously. Yeah? So that is the first case where we substitute last of Q by last of S. The second part here, what could we do as the second option? Well, we could insert last of S into Q. Yeah? So Q remains unchanged, and we insert last of S into Q, so to say. So what we need to do next is, well, first of all, we have again one insert operation, so one edit operation, so it's one plus. And what is the rest, what we have to do? Well, we have to match the entire Q, because we just inserted something. We didn't touch, we didn't do anything with Q so far. We just inserted something, but we didn't use the elements of Q, the original elements of Q. So we have to align the entire Q to the prefix of S, because we already inserted the last S. Yeah? So that is the second case here. So we have this additional operation, this one operation for the insert. And then we have to map or align the entire Q to the prefix of S. Yeah? And the third option that we have is we could, in order to transform Q into S, we could delete the last Q. Yeah? And what else do we have to do? Well, we have then to map or to align the prefix of Q to the entire sequence S. And that is the third part here. So this one here again is the operation for the delete. And what we have to do then next is to map or to align the prefix of Q to S. Yeah? So that is the third case here. So we have these three options. In all of these three options, this is only the case, obviously, what we just said, when the last elements are different. So we have these three options. In all of those three options, we have one edit operation, which is this one here, plus the cost that we have for the remaining matches. And of course, since we want to have as the edit distance the minimum number of edit operations, we look for all of those three options. From all of those three options, we look for the one that have the minimum number of edit operations. Yeah? So we take one, which is the edit operation we did for the last element, plus the minimum of these three options here. Yeah? And that is the most important part here of this recursive formula. Yeah? Okay, so that sounds a little bit nasty, because if in this else case here, which is the case when the whole thing doesn't match, we need to actually examine three recursive calls. Yeah? So if we take a look at how to compute that in a naive way, so here is an example with two sequences. Well, first of all, we see the last elements here of the first and the second sequence, they don't match. Yeah, so we are in this second recursive case. We have 1 plus and then the 3 options. So we have to compute all the 3 options. We have to compute all the 3 recursive calls to see what is actually the minimum. Yeah? So we have the substitution case, we have the insertion case, and we have the deletion case. And you see that all of those cases here may also end up in a recursive call. Yeah? So if we consider the worst case, obviously, well, in the worst case, in each recursive call, so for each element in both of those two sequences, we have 3 recursive calls always. That is the worst case. So we don't have the worst case here, obviously, but here we have again 3 recursive calls, and so on and so on and so on. So the worst case is that in each recursive call we have 3 options. And how many recursive calls do we have? Well, we have for each element we have recursive calls. So this ends up in, well, in this kind of search tree here, which have a height of 3 to the power of n plus m. Yeah? So the naive computation, the complexity of the naive computation would have O of 3 to the power of n plus m, which is of course a lot. Yeah, so that is somehow not acceptable for larger n and m's. Yeah, so for longer sequences, we cannot do that. We cannot afford that. That's too much. Yeah? Well, if we analyze this naive computation a little bit closer, we'll see that there is some kind of overhead, some kind of redundant overhead that we do. Well, first of all, we just agreed that we have this 3 to the power of n plus m function calls in the worst case for the sequences of length n and m. But if we look closer to this here, we see that a lot of those function calls are actually redundant. So this here is the same as this, this one here. And well, do we have other things like here? Yeah. Well, anyway, look at that a little bit closer and think about it. A lot of those recursive calls will be the same. Yeah, will be redundant actually. Yeah. So a lot of those calls appear repeatedly. And actually, if we think about it, well, we want to align m elements from the first, from the second, or from the first one, whatever, from one of this sequence of length m to all of the elements of length n. So how many different possibilities do we have? Well, actually, we could just permutate everything more or less the same, but we cannot really permutate completely. So there are obviously only m plus 1 times n plus 1 different recursive calls, different alignments that we can compute here in these calls here. Yeah. I just told you something wrong. So the height of the tree is not 3 to the power of n plus m. That's so many calls. The height actually is n plus m, because we actually go through n plus m many, in the worst case, elements, and for all of those we have in the worst case 3 recursive calls. So the height of this tree here is n plus m, and since we have a fan of 3, we have 3 to the power of n plus m, many different nodes in this tree. That's the point. Yeah. So the number of nodes here in the tree is O to the power of 3. O of 3 to the power of n plus m. Yeah. So that's the point. But the height of the tree is n plus m, or O of n plus m. Actually, it's n plus 1 times m plus 1. Yeah. So we have so many different recursive calls. So the solution to getting down from O of 3 to the power of n plus m to O of m times n, which is much less obviously than this one here, still a lot, but much less than this one here, is the solution is to store the results of the calls that we already computed actually. yeah, because we need some of those calls maybe repeatedly, so we just store the results and don't compute them always on the fly, so to say. Yeah. The downside is that it requires m times n space, obviously, yeah. But if we do that, we can dramatically reduce the runtime. Yeah. So the systematic evaluation of these m times n operations can be done if we store those results, if we store those intermediate results, so to say. And this scheme to systematically evaluate these operations is called dynamic programming. You probably already know, but yeah, you can apply that here for the computation of the edit distance. And this makes a huge difference, as you see here in this illustration of the acceleration. So here the example is for two sequences of length 5, of length 50, and of length 500. You see that in terms of the speed up here, you have with the dynamic programming 25 computations instead of 3 to the power of 5 plus 5, which is 10, which is almost 60,000 computations. Yeah, so 25 instead of 60,000. And of course, it gets really weird if you just go up with the length of the sequences, as you see here. Yeah, so for 50, you have 2,500 computations instead of 3 to the power of 100, which is, well, I cannot even number that or call that, actually name that actually here, and so on and so on and so on. Yeah, so the acceleration is, yeah, I would even call that ridiculous. Yeah, so that is a really huge improvement in terms of performance, of course. Yeah, so you absolutely are okay with this additional space requirements, which are of course also m times m in that case.